So here's the thing about the moon. We basically abandoned it. And I don't mean we stopped visiting. I mean, we went there, planted some flags, collected some rocks, and then just left for 50 years. Not because we couldn't go back, but because we decided there wasn't a good enough reason to spend the money. And then something changed. Someone at NASA looked at the budget spreadsheet, looked at what China was doing, looked at what private companies were starting to pull off, and thought, okay, we need to actually finish this. That's where Artemis comes in. But here's what's weird about Artemis: it's not actually a comeback story. It's more like someone finally admitting they never actually finished what they started in the first place. When people think about going to the moon, they picture Apollo. They picture Neil Armstrong, the grainy footage, the conspiracy theories that won't die. But Artemis is something different. It's boring in a lot of ways. There's no single hero moment. There's no race against the Soviet Union. There's just a lot of engineers trying to solve a problem that sounds simple, but is genuinely complicated. And the thing that most people don't realize is that going to the moon the second time is actually harder than going the first time. Let me explain why that matters, because it actually changes everything about how you should think about this program. The first moon landings happened in this weird window where the technology was almost primitive enough that it could work, but also advanced enough that it actually did work. The Saturn V rocket, which is still, by the way, the most powerful rocket ever successfully flown, was built with computers that had less processing power than a modern calculator. Engineers did the math with slide rules and coffee. There was this beautiful simplicity to it. You build the biggest, most powerful thing possible, you strap people to it, and you hope the math works out. Artemis can't work that way. The budget won't allow it. The political will won't allow it. And honestly, we've learned enough about physics and engineering that we don't have to work that way anymore. So instead, Artemis is built on something that sounds way less dramatic, but is actually way more interesting: efficiency. The whole program is structured around this idea of sustainability, which I know that word gets thrown around a lot, and usually it's meaningless corporate speak. But in this context, it actually means something specific. It means building a system where you can go to the moon repeatedly without bankrupting your country or waiting 50 years between trips. It means creating infrastructure. It means treating the moon like a destination, not like a stunt. And that changes literally everything about how you design the missions. Apollo 11 landed on the moon for like 22 hours. The astronauts collected some rocks and left. That was the whole mission. In and out, fast and dramatic. Artemis 3, which is the mission where actual humans will land on the moon again, is designed for much longer stays. We're talking about astronauts spending days on the surface. Days, which means they need more supplies, more equipment, better habitats, ways to deal with the radiation that Apollo astronauts basically just accepted, which is kind of wild when you think about it. Here's an obscure fact that actually illustrates how different these missions are. The Apollo astronauts received radiation doses during their trips to the moon that, if they'd received them on Earth, would have required immediate medical attention. We're talking about doses that increase cancer risk measurably. We just didn't really talk about it at the time, which is maybe the most 1960s response to a serious problem imaginable. But Artemis has to account for radiation protection because the missions are longer and because, well, we know better now. The architecture of Artemis is actually fascinating because it's basically a rejection of how Apollo worked. Apollo was designed around one big rocket, one spacecraft, boom, you're on the moon. Artemis is designed around multiple launches, multiple components that have to dock together, a space station that has to stay in orbit as a jumping off point. It sounds more complicated because it is more complicated, but it's actually more flexible and more capable. The centerpiece of all this is the Space Launch System, or SLS. Wait, before I explain what this is, I want to be clear about something. The SLS is controversial, like genuinely controversial. There are smart people in the space industry who think it's a waste of money and that private companies like SpaceX could do this cheaper and faster. And honestly, they might be right. But that's kind of missing the point of why the SLS exists in the first place. The SLS was designed to be built with existing infrastructure and existing contractors, which means Boeing, Lockheed Martin, the big companies that already have relationships with NASA. And yes, that's partly political. Congress wanted jobs in their districts. That's just true. But it's also practical because these companies have experience building large-scale space hardware. The SLS is basically the evolution of the Space Shuttle program, which means it's built on decades of accumulated knowledge about how to build really big, really complicated machines that have to work in space. Here's the thing about the SLS that people don't always understand. It's not a single rocket. It's a family of rockets. The baseline version is called Block 1, and it's designed to put about 27 metric tons of payload into lunar orbit. But there's also a Block 1B version being developed that could put up to 84 metric tons. And then there's the Block 2 version, which theoretically could put over 130 metric tons into orbit. That's more than 3 times the capacity of the baseline version. So the idea is that you're building a system that can scale up as you need it. Except here's the problem with that plan. Building rockets is phenomenally expensive. Each SLS launch costs somewhere in the neighborhood of $2 billion. Maybe more. Estimates vary because the program keeps changing and costs keep going up. For context, SpaceX is launching the Falcon Heavy for around $90 million. That's a satellite launch price, so it's not a perfect comparison, but it illustrates why people are skeptical about the SLS business model. But wait, there's something more interesting going on here that actually justifies some of the expense. The SLS is designed to be human-rated. That means it's built to a standard where the failure rate has to be incredibly low because there are people sitting on top of it. The Falcon Heavy, when SpaceX uses it for human missions, gets upgraded to human rating standards too. But the process of human rating is expensive and time-consuming because you have to test everything multiple times and document everything extensively, which is why the SLS costs what it costs. And here's where it gets weird. The SLS might actually be cheaper in the long run than using commercial rockets for human missions, depending on how you calculate it. If SpaceX had to launch the Falcon Heavy to human rating standards every single time, the price would go up. So comparing the sticker price of an SLS launch to a commercial launch price isn't really apples to apples. That said, SpaceX is developing the Starship, which is designed to be bigger, more powerful, and cheaper than the SLS. And it might actually deliver on those promises, in which case the entire logic of the SLS becomes questionable. But that's a problem for future NASA administrators to worry about. Right now, the SLS is what exists, and it's what Artemis is built around. So the SLS launches this capsule called Orion, and Orion is basically the heir to Apollo Command Module design, except it's bigger, more capable, and way more modern. Orion can carry 6 astronauts, though the Artemis missions are planned with 4. It has a heat shield that can handle entry speeds from the Moon, which are much faster than entry speeds from low Earth orbit. An obscure fact: the Apollo Command Module's heat shield was designed to handle re-entry speeds of about 11 kilometers per second. but returning from the moon means you're coming in at about 11.2 kilometers per second, which sounds like a tiny difference, but the energy difference is actually significant. It's one of those physics things where small changes in velocity create massive changes in energy, because kinetic energy goes up with the square of velocity. Orion sits on top of the SLS, and when you launch it, the whole thing goes straight to the moon. No low Earth orbit parking, no docking in LEO. Straight shot. The idea is that you're burning fuel to get there, but you're saving time. And for human missions, time can actually be safety. The longer astronauts are in space, the more radiation they're exposed to, the more time for something to go wrong with the spacecraft. But here's where the architecture gets interesting. Orion by itself can't land on the moon. It's designed to orbit the moon and drop off a lander, which means you need a separate lander. And not just any lander. You need a lander that's big enough for 4 people, that can stay on the surface for multiple days, that can handle the radiation environment, and that can launch back off the moon to rendezvous with Orion. That lander is being developed by a company called Dynetics, though there's also a version being developed by a consortium led by Blue Origin. And here's an interesting tidbit. These aren't small companies building these landers. Blue Origin has Jeff Bezos' money behind it. Dynetics is part of Leidos, which is a massive defense contractor. SpaceX, which isn't directly building the primary lander for this mission, but is in competition for future contracts, is building Starship, which could theoretically land people on the moon too. So what you have is this weird situation where multiple companies are building multiple moon landers, and NASA is trying to figure out which one is best, which sounds inefficient but actually makes sense from a risk management perspective. If you're committing to going to the moon and you want that mission to succeed, you want options. You want different approaches that could work. The lander design is actually where a lot of the innovation is happening. Unlike Apollo landers, which were designed for a single mission with a single crew, these new landers are designed for multiple missions. They're supposed to be reusable, which means they need better thermal management, better structural integrity, better systems for handling the heat of launch and landing multiple times. Here's an obscure fact that shows how much harder this is than Apollo. The Apollo lunar module was designed to land on relatively smooth terrain because the astronauts had limited control. The guidance computer couldn't handle complex terrain recognition, so they aimed for flat areas. But we've learned a lot more about the moon in the past 50 years, and we know there's a lot of interesting science in rough terrain. Mountains, craters, places where ice might be hiding. So the new landers have to be capable of navigating rough terrain, which means better sensors, better landing algorithms, better structural design to handle irregular surfaces. The other thing about the new landers is that they're going to the south pole of the moon, which is different from Apollo. Apollo landed near the equator, partly because the trajectory was easier, partly because we had less information about the poles. But the South Pole is interesting because of water ice. And this is where the science gets genuinely fascinating. For decades, we suspected there might be water ice on the moon, but it wasn't until we sent orbiters with sophisticated instruments that we got confirmation. There are permanently shadowed craters at the poles where the temperature never rises above about minus 170 degrees Celsius. In those craters, water ice can exist indefinitely, which is a huge deal because water is useful. You can break it down into hydrogen and oxygen, which is rocket fuel. You can use it for drinking water. You can use it for radiation shielding. If you're trying to build a sustainable presence on the moon, water ice is like finding oil. Here's another obscure fact. The water on the moon might have come from multiple sources. Some of it probably came from asteroid impacts. Asteroids that contain water or organic compounds hit the moon and left behind water ice. But some of it might have been created by solar wind. The sun is constantly streaming protons toward the moon, and some of those protons interact with oxygen in the lunar regolith to create water molecules. It's not a lot, but over billions of years, it adds up. So the moon is literally making water from solar wind and dirt, which is kind of poetic in a nerdy way. The Artemis missions are specifically designed to search for and map this water ice, which requires different instruments, different landing sites, different scientific priorities than Apollo had. And that's actually the thing I think people underestimate about Artemis. It's not about recreating Apollo, it's about doing something different. Let me talk about the timelines because this is where reality meets expectation. Artemis 1 was an uncrewed test flight that finally happened in November 2022. It launched the SLS for the first time, sent Orion to the moon and back, and proved that the basic architecture works. The mission lasted about 26 days, and Orion went further from Earth than any crewed spacecraft has ever gone, about 400,000 kilometers out, which was beyond the moon, which was beyond anything Apollo did. Artemis 2 is supposed to happen sometime in 2025 or 2026, and it will be crewed. 4 astronauts will fly to the moon and back, but they won't land. They'll orbit the moon, do some science, test systems, and come home. It's basically a dress rehearsal for the landing mission. Artemis 3 is where people actually land on the moon again. That's supposed to happen in 2026 or 2027, though honestly, these timelines have slipped before, and they'll probably slip again. Space projects are like that. You're trying to coordinate thousands of engineers across multiple companies. You're building things that have never been built before, and you're working with politics and budgets that change every 4 years when a new administration comes in. So when NASA says 2026, what they probably mean is sometime in the late 2020s, give or take. But here's what's actually happening between now and then. That's interesting. There's this whole infrastructure being built up around Artemis that doesn't get as much attention as the rockets and landers, but it's genuinely important. The first piece of that infrastructure is called the Lunar Gateway. And the name is kind of a misnomer because it's not really a gateway in the sense of being on the moon. It's more like a space station that orbits the moon. The idea is that you launch Orion to the gateway, dock with it, and then use it as a staging point to send a lander down to the surface. This allows you to have more flexibility in where you launch from and when you launch from, because you're not committed to a single trajectory. The gateway is being built by an international consortium. Japan is contributing part of it. Europe is contributing part of it. Canada is contributing part of it, which is actually significant because it means that Artemis isn't just a NASA program. It's an international program which changes the politics and the funding and the long-term sustainability. If multiple countries are invested in the gateway, then it's harder for any single country to just cancel it when a new administration comes in. Here's an obscure fact about the gateway. It's being designed to eventually host a crew of 4 people for extended periods, like weeks at a time, which means you need habitat modules, life support systems, power systems, communication systems. You basically need a small space station. And you need to build all of this in lunar orbit, which is a really weird place to operate. It's far enough from Earth that communication has a significant delay, about 2.5 seconds one way. It's far enough from the moon that you can't just rely on the moon's gravity for stability. You're in this weird in-between place. The power systems for the gateway are interesting because you can't rely on solar panels the way you do in low Earth orbit. The gateway's orbit passes through the Earth's shadow sometimes, so you need batteries or you need some other way to generate power. The current design uses solar panels with a really good battery system, but there's been discussion about using nuclear power in the future, which sounds dramatic, but actually makes sense for deep space exploration. Nuclear is reliable, compact, and doesn't depend on where you are relative to the sun. Now, the other piece of infrastructure that's less visible but equally important is the ground systems. You need tracking stations all over the world to communicate with the spacecraft. You need computers to run the simulations and the training. You need facilities where astronauts can practice. NASA has been investing in all of this, updating old equipment from the space shuttle era, building new facilities. It's not as exciting as a rocket launch, but it's just as necessary. The astronauts for Artemis are interesting because they're different from the Apollo astronauts in some fundamental ways. The Apollo astronauts were mostly military test pilots. They were all men. They were selected for a very specific kind of profile. The Artemis astronauts are a more diverse group. There are women, which is new. The first woman to walk on the moon will be part of Artemis. There are people from different backgrounds and different career paths. NASA actually made a conscious decision to open up the astronaut selection process to people who weren't necessarily military pilots, which was a big change. And this matters because it changes who gets to go to the moon and who gets to contribute to that mission. For 50 years, the moon was the domain of a very small, very specific group of people. Now it's opening up, which is partly about representation and partly about practical skills. You don't necessarily need a military test pilot background to be a good moon explorer. You might need a geologist, a physicist, an engineer with different expertise. So opening up the selection process actually makes the missions better. Here's an interesting historical note. When NASA was designing the Artemis astronaut selection, they specifically wanted to ensure that the first woman to walk on the moon would be part of this program. Not as an afterthought, but as a core part of the mission design, which is a different approach than Apollo, where women weren't even allowed to apply to be astronauts until 1978, which was 9 years after the last Apollo moon landing. So there's this weird historical irony where the moon exploration program that started in the 1960s with exclusively men is coming back with women as a core part of the next phase. Progress, but also, it took 50 years. The training for Artemis astronauts is intense in ways that are different from Apollo training. Apollo astronauts trained in the Arizona desert because the terrain is similar to the moon. Artemis astronauts train there too, but they also train in analog environments that simulate other aspects of the mission. There's a facility in Hawaii where they train in lava tubes because the moon might have lava tubes that could be useful for habitats. There's underwater training in neutral buoyancy, which simulates the weightlessness of space. There's extensive simulator training because you want astronauts to be familiar with every system and every contingency. An obscure fact about astronaut training: it's one of the most dangerous jobs even before you get in the rocket. Astronauts have died in training accidents. The Apollo 1 fire killed Gus Grissom, Ed White, and Roger Chaffee in a launch pad test. More recently, astronauts have had close calls in training scenarios, so the training itself requires safety protocols and contingency planning, which is kind of meta. You're training people to handle emergencies in space by sometimes creating realistic emergency scenarios in training. Now, let's talk about what the astronauts are actually going to do on the moon, because this is where the science gets really interesting. The Artemis missions have specific scientific objectives. They're not just going to plant flags and take pictures, though they'll do that too. They're going to do actual scientific work. The primary objective is to find and characterize water ice, which means taking samples, analyzing them, understanding their distribution and their accessibility. If we're going to build a long-term presence on the moon, we need to understand water resources. Where is it? How pure is it? How easy is it to extract? These are practical questions, but they're also scientifically interesting because they tell us about the moon's geology and history. The secondary objectives include studying the radiation environment. Remember how I mentioned that Apollo astronauts received radiation doses? We want to understand the radiation environment on the moon so we can design better protection for future missions. We also want to look for organic compounds, the molecules that are the building blocks of life. The moon has meteorites that fell from asteroids, and some of those asteroids contain organic material. So by studying the moon, we're studying materials from the early solar system, which tells us about how the solar system formed. There's also the search for volatiles, which is a fancy term for stuff that evaporates easily. Besides water ice, there might be methane ice, carbon dioxide ice, nitrogen ice, and other frozen gases in those permanently shadowed craters. Why does that matter? Because volatiles are clues to the moon's history. They tell us about impacts, about the solar wind, about geological processes that we don't fully understand yet. The astronauts will also be collecting samples for return to Earth, which is different from automated rovers or landers. A human can make judgments about what's scientifically interesting. A human can adapt to unexpected discoveries. A human can do things with intuition and experience that a robot can't. That's the advantage of human exploration. You get flexibility and judgment that you can't get with remote control. Here's an interesting psychological aspect of moon exploration that doesn't get talked about much. The astronauts are going to be on the surface for multiple days, and they're going to be far from home. Apollo astronauts reported profound emotional responses to being on the moon. Some of them experienced something close to awe or transcendence. They talked about the fragility of Earth when seen from the moon, about the perspective it gave them on humanity and our place in the universe. That's not just sentimental, it's a documented psychological phenomenon. And it matters because it affects how astronauts interact with their experience and how they communicate that experience back to Earth. Now let's talk about the international aspect of Artemis because this is significant and also contentious. NASA has been building what's called the Artemis Accords, which is basically a set of principles for how countries should conduct lunar exploration. It includes things like peaceful exploration, compatibility with international law, and commitments not to claim territory on the moon. And a bunch of countries have signed on: Japan, Canada, Australia, UAE, and others. But here's the thing. Not everyone has signed the Artemis Accords. China hasn't. Russia hasn't. And those are the countries that are also developing their own lunar exploration programs, which means there's potential for conflict or competition on the moon, which is interesting because the moon is supposed to be the province of all mankind, according to the Outer Space Treaty of 1967. But enforcement of that treaty is vague, and the economic and strategic incentives for lunar exploration are real. Here's an obscure fact that illustrates this complexity. There's actually an argument about what counts as a landing on the moon. If China lands a spacecraft on the moon but doesn't have astronauts, does that count? If a private company lands, who gets credit? There's no international authority that decides these things. It's basically a Wild West situation, which is kind of fascinating in a geopolitical sense. The United States is trying to establish norms for lunar exploration through the Artemis Accords. The idea is that if you agree to these principles, you get access to resources, technology, and international cooperation. If you don't agree, you're outside the tent. It's a soft power play, but it's also substantive because lunar exploration is expensive and you need partners to make it work long term. But here's where it gets complicated. Even within the Artemis coalition, there are tensions. International partners are investing in Artemis infrastructure, but they also want to make sure they're getting value from that investment. Japan is contributing modules to the gateway, but they also want assurance that they'll have opportunities to do their own missions. Europe wants to be involved in decision-making about where the gateway goes and what it does. Canada has astronauts who want to go to the moon. So NASA is managing all these relationships while trying to keep the program on track and on budget, which is, well, it's politics, and politics is complicated. One of the interesting dynamics is that SpaceX is involved in Artemis in an indirect way. SpaceX isn't building the SLS, but SpaceX is contracted to help with some aspects of lunar logistics. Specifically, SpaceX is developing a lunar lander called Starship that could eventually be used to bring cargo to the moon, or potentially support crewed missions. And Starship is a completely different design philosophy from the traditional aerospace approach. Starship is huge, taller than the Saturn V rocket, and designed to land on its tail using engines. It's a radical design that most traditional aerospace engineers were skeptical about, but SpaceX is actually demonstrating that it can work. And if it does, it changes everything about lunar logistics because Starship has huge cargo capacity. Instead of small landers that can carry a few people, you could have landers that carry tons of equipment, or habitats, or mining equipment, or whatever you need. This is where it gets really interesting because it suggests that the future of lunar exploration might not be built on the traditional aerospace contractor model that built the space shuttle, and that's building the SLS. It might be built on commercial companies with different approaches and different incentives, which would be more disruptive and also potentially more efficient. But here's the thing, we don't know yet. Starship hasn't actually landed on the moon. SpaceX is still developing it. So while it's theoretically capable of revolutionizing lunar logistics, it hasn't proven it yet. And Artemis can't wait for theoretical capabilities. It has to move forward with known systems. Let me talk about the risks and the things that could go wrong, because space exploration is actually incredibly risky, and people tend to underestimate that. The SLS has been in development for over a decade, and it's only flown once. That's a long development cycle, and every time you fly a new rocket for the first time, there's risk. The engines could fail. The structural integrity could be compromised. There could be software issues. There could be weather delays that cause problems. There could be supply chain issues. Any of these could delay Artemis 2 or Artemis 3 indefinitely. The Orion spacecraft has to work perfectly because people are sitting on top of it. If the heat shield fails on re-entry, the spacecraft burns up with the astronauts inside. If the life support system fails, the astronauts run out of oxygen or water or the right atmosphere to breathe. If the communication systems fail, mission control can't talk to the crew. These are all single points of failure that have been engineered with redundancy in testing, but redundancy and testing don't eliminate risk. They just reduce it. The landers have to work on a surface that's hostile in ways that Earth isn't. The temperature swings between plus 120 degrees Celsius in the sunlight and minus 170 degrees in the shadow. The regolith, the lunar soil, is abrasive and sharp at the microscopic level. It sticks to everything. It damages seals and scratches optical surfaces. The gravity is 1/6 of Earth's, which means the landing dynamics are different. An obscure fact: lunar dust might actually be toxic to humans. We don't fully know because only a small number of people have been exposed to it, and they were only exposed briefly. But some research suggests it might cause inflammatory responses in the lungs or skin. So astronauts could be landing on a surface where they have to wear protective gear, not just for radiation, but for dust exposure. There's also the problem of communication delays. The moon is about 385,000 kilometers from Earth. Radio signals travel at the speed of light, so it takes about 1.3 seconds for a signal to get from Earth to the moon. That means if mission control tries to warn an astronaut about a problem, there's a 2.6-second delay before the astronaut can respond. That's not a lot of time, but it's enough that astronauts have to be trained to make independent decisions and troubleshoot problems on their own, which is why the training is so intense. There's also the radiation problem that I mentioned earlier. The moon isn't protected by a magnetic field like Earth is, so the surface is exposed to solar radiation, cosmic rays, and radiation from the Van Allen belts that extend further from Earth than previously thought. An astronaut spending days on the moon is going to get a radiation dose that increases their cancer risk. NASA has calculated acceptable radiation doses for astronauts, but there's always uncertainty in these calculations. We don't know exactly how sensitive individual humans are to radiation. We have statistical models, but individuals vary. Another risk is psychological. Being on the moon is a psychologically intense experience. You're far from Earth, you're in an alien environment, you're dependent on your equipment and your training and your crewmates. If someone has a psychological breakdown on the moon, you can't just send a rescue mission. You have to get the person to the lander and launch them back to orbit. You have to handle the situation with the resources you have on site. So NASA selects astronauts carefully for psychological resilience, and they train extensively for emergency scenarios. But you can't eliminate human psychology. There's also just the sheer complexity of the mission. Artemis 3 involves launching the SLS, launching supply missions or cargo missions, getting everything to the gateway, sending a lander down to the surface, keeping the astronauts alive for multiple days, getting them back to the lander, launching them back to orbit, rendezvous with Orion, and then returning to Earth. Each of those steps is a complex operation with multiple components that have to work. The probability of everything working perfectly on the first try is low. There will probably be problems. The question is whether those problems are solvable or whether they're critical failures. This is why NASA does so much testing and simulation. They build test articles, physical mock-ups of spacecraft and systems, and they test them under as close to actual conditions as possible. They run simulations where astronauts practice dealing with emergencies. They test components until they fail and then redesign them to handle more stress. It's expensive and time-consuming, but it's necessary because the stakes are high. Now let's talk about the long-term vision for Artemis, because the landing missions are just the beginning. NASA and other space agencies have been talking about building a sustained presence on the moon, which means permanent or semi-permanent bases, equipment left on the surface that can operate for months or years, infrastructure for mining or construction, eventually human settlements. This is where things get speculative, but it's also where things get interesting. If you can build a base on the moon, you can do science that you can't do from Earth. You can observe the universe from the far side of the moon, which is shielded from radio noise from Earth. You can use lunar resources to build things, which might be cheaper than launching everything from Earth. You can use the moon as a stepping stone to Mars or deeper space exploration. An obscure fact: some researchers have proposed building radio telescopes on the far side of the moon. Because the far side is shielded from Earth's radio noise, you could build incredibly sensitive instruments that could detect very faint radio signals from distant galaxies or even search for extraterrestrial signals. This is speculative, but it's a real scientific opportunity that only becomes possible with a presence on the moon. There's also the question of mining. The moon has resources: water ice, metals, rare earth elements. If you could extract these resources and use them, either on the moon or to ship to Earth, you could theoretically make space exploration cheaper. You could build spacecraft from lunar materials instead of launching everything from Earth. This is mostly theoretical right now because we don't know how to do mining on the moon at scale, but people are thinking about it and planning for it. Here's another obscure fact. The moon might have helium-3, which is a rare isotope of helium. On Earth, helium-3 is extremely rare and very expensive. But on the moon, it's more abundant because it accumulates in the regolith from solar wind over billions of years. Helium-3 has potential applications in fusion reactors. If fusion energy becomes practical, and if helium-3 becomes valuable, the moon could become a source of fuel. This is very speculative. We don't have practical fusion reactors yet, but it's the kind of long-term thinking that drives lunar exploration. The idea of a lunar base also raises questions about what that base would look like. Would it be a small outpost with just a few people? Would it be a larger settlement with dozens of people? Would it be automated, with robots doing most of the work? Would it be partially underground, taking advantage of natural caves or lava tubes? An interesting proposal that's been discussed is using lava tubes as habitats because they would provide natural radiation shielding. The lunar surface is exposed to radiation, but underground structures would be protected by the rock above them. Building structures on the moon has its own challenges. The regolith doesn't have the cohesion of soil on Earth. It's very fine and doesn't pack tightly. So building a concrete structure on the moon would be different from building on Earth. Some proposals involve using the regolith as a building material directly, either by sintering it with heat or by mixing it with a binder. Other proposals involve bringing materials from Earth. It's an engineering problem that doesn't have a solved answer yet. The dust problem I mentioned earlier becomes critical if you're trying to build a long-term presence. The dust gets into everything. It damages equipment. It affects visibility. It might be toxic. So any long-term base would need dust management systems, ways to keep equipment clean, ways to prevent dust from entering habitats, ways to protect people from dust exposure. There's also the question of water extraction. If you're building a base on the moon and you want to use water ice as a resource, you need equipment that can drill or excavate the regolith, extract the water, and refine it. This is all theoretical right now because we haven't actually tried to do it on the moon, but it's something that engineers are designing and planning for. Now, let's talk about the economics of all this, because this is where the rubber meets the road. Artemis is expensive, really expensive. NASA's budget for Artemis over the next decade is something like $100 billion. That's a massive amount of money. For context, that's roughly equivalent to the annual budget of the Department of Education. So we're talking about a significant commitment of national resources. The question is whether that's worth it. And that's where people disagree. Some people think lunar exploration and space exploration in general are worth the investment because of the scientific knowledge, the technological advancement, the inspiration it provides. Other people think the money would be better spent on problems on Earth: poverty, disease, climate change, education. Here's the thing about that argument: it's not really an either or situation. NASA's budget is about 0.5% of the federal budget. If you eliminated NASA entirely, you wouldn't solve poverty or disease or climate change. The money wouldn't automatically get redirected to those problems. But it's still a fair question to ask whether the resources are being allocated in the best way. One argument for Artemis is that space exploration has economic returns. The technologies developed for space exploration get used on Earth. The Apollo program led to advances in materials, computing, medicine. Satellite technology, developed for space, revolutionized communications. GPS, initially a military system developed partly for space applications, became essential infrastructure. The argument goes that investing in space exploration pays dividends in technological advancement. Another argument is that space exploration inspires people, especially young people, to pursue careers in science and engineering. There's data suggesting that major space missions increase interest in STEM education, and STEM skills are valuable in a modern economy. A third argument is that space exploration is humanity's future. Eventually, Earth won't be able to support all of humanity, or resources will become scarce, or climate will become unstable. The argument goes that we need to develop the capability to expand beyond Earth. The moon is a stepping stone to that future. But here's the counter-argument: those benefits are speculative and long-term. The costs are real and immediate. Money spent on Artemis could be spent on problems that are urgent and measurable. Climate change is happening now. Poverty is happening now. Artemis 3 will land on the moon sometime in the late 2020s, maybe. That's years away. What's interesting about this debate is that it's actually a values question, not a purely economic question. People who value exploration and scientific advancement lean towards supporting Artemis. People who prioritize addressing immediate social problems lean against it. There's no objectively correct answer because it depends on what you think humanity's priorities should be. What I think is interesting is that Artemis exists in this weird space where it's politically viable because it's been around for a while and has bipartisan support. Congress has continued to fund it despite budget pressures, which suggests there's some consensus that it's worth doing. But that consensus is fragile and dependent on the program delivering results. If the SLS keeps experiencing delays, if costs keep going up, that consensus could crack. This is where the commercial space industry becomes relevant again. If SpaceX or Blue Origin or another company can demonstrate that they can do lunar missions cheaper and faster than NASA, there will be pressure on NASA to change course. And actually, that might be healthy. Competition can drive efficiency, but it also means the future of lunar exploration might not be government-led. Here's an interesting wrinkle. NASA has been moving toward a commercial model for human spaceflight. The Commercial Crew program contracted with SpaceX and Boeing to develop spacecraft that carry astronauts to the International Space Station. That worked reasonably well. SpaceX is flying regular crew missions now. NASA is trying to do something similar for lunar logistics through a program called Commercial Lunar Payload Services, or CLPS. The idea is that private companies will provide transportation to the moon, and NASA will contract with them to deliver cargo and experiments. This is actually a smart approach because it creates a market for lunar services. If multiple companies are offering lunar delivery services, competition will drive prices down and innovation up. It also takes some of the burden off NASA to design and build everything. But it also creates complexity because now you have NASA managing contracts with multiple commercial providers, and you have to make sure their systems are compatible with each other and with NASA's systems. You have to coordinate schedules and priorities. It's an engineering and management problem, but it's also a potentially more sustainable model for long-term lunar exploration. Let me talk about what's actually happening right now in 2026, because this is where we are currently. Artemis 1 flew in 2022, and it was successful. The SLS works. Orion can make the journey to the moon and back. That's proven. Artemis 2 is supposed to fly soon, within the next year or so from when I'm writing this. It will carry 4 astronauts to the moon and back, but they won't land. That's going to be a significant moment because it will be the first time humans have been to the moon since 1972. That's 54 years. That's more than half a century. An entire generation of humans has been born and grown up without anyone walking on the moon. When Artemis 2 flies, it's going to be a big deal. The media will cover it extensively. There will be live launches and splashdowns. There will be astronauts talking about their experience. For people who weren't around for Apollo, it will be the first time they've experienced a major human spaceflight event like this. And then Artemis 3 comes after that with the actual landing mission. And that's when things get really interesting because you have astronauts on the surface of the moon for multiple days, doing science, collecting samples, exploring. That's the moment where lunar exploration really starts again. Beyond Artemis 3, there's been discussion about Artemis 4, 5, and 6, additional missions that would establish a more sustained presence on the moon. But those are further out and less certain. Budget priorities could change. Political priorities could change. Technology could change. So while there's a vision for sustained lunar exploration, the actual commitment beyond Artemis 3 is somewhat uncertain. Now let's talk about some of the specific science that Artemis will be doing, because this is where the missions get fascinating for people who care about actual understanding, not just the spectacle of going to the moon. The search for water ice is probably the most high-profile scientific objective. The Lunar Reconnaissance Orbiter, which is an orbital spacecraft that's been mapping the moon since 2009, has identified locations where water ice is likely to exist. These are primarily in the permanently shadowed craters near the poles. The Artemis missions will land near these locations and will try to collect samples. Here's what's interesting about water on the moon. We didn't know it was there until the 2000s. The Apollo astronauts didn't find any water. They brought back samples of dry lunar rock. So for decades, people thought the moon was completely dry. But then we sent orbiters with more sophisticated instruments, and we detected signatures of water. Specifically, we detected absorption spectra that matched water or hydroxyl groups, chemicals that contain hydrogen and oxygen bonded together. There are different ways to detect water from orbit. You can look for absorption spectra in visible or infrared light. You can look for neutron signatures that indicate hydrogen in the surface. You can look for radar dark regions that might indicate water ice. Different instruments use different methods, and they all point to water existing on the moon in places where it can be permanently frozen. An obscure fact: the amount of water on the moon is probably millions of tons. Some estimates suggest there could be billions of tons in the polar craters alone. That's a lot of water. If even a fraction of that is accessible, it changes the economics of lunar exploration. You could use it for fuel, for life support, for radiation shielding. it's a game changer. But there's a catch. The water is mixed with regolith. It's not like there's ice in a crater that you can just scoop up. It's distributed through the soil at various concentrations. Some estimates suggest concentrations as low as 0.5% water by weight. Other estimates suggest higher concentrations in certain areas. But extracting that water requires processing large amounts of regolith, which requires equipment and energy and time. The Artemis astronauts will be drilling and collecting samples to understand the distribution and concentration of water in different locations. They'll be taking samples of regolith and bringing them back to Earth for detailed analysis. They'll be using instruments to measure in situ water content. The data they collect will inform future missions and future engineering of water extraction systems. There's also the question of organic compounds. The moon has meteorites that came from asteroids and other objects. Some of these meteorites contain organic compounds, carbon-based molecules that are the building blocks of life. They're not alive, but they're chemically complex and scientifically interesting. Understanding what organic compounds are on the moon tells us about what materials were available in the early solar system, and that tells us about the chemistry that led to life on Earth. An obscure fact: some meteorites that fall on Earth come from the moon. Lunar meteorites are ejected by impacts on the moon. They travel through space, and some of them eventually hit Earth. We've collected lunar meteorites on Earth, and they've given us information about the moon's geology without having to send samples back from the moon. But there are probably materials on the moon that haven't been ejected as meteorites yet, and those could be scientifically interesting. The radiation environment is another key scientific objective. The moon doesn't have a magnetic field, so the surface is exposed to solar radiation and cosmic rays. But the intensity and type of radiation varies depending on location and solar activity. Understanding the radiation environment is important for future human missions because we need to know what radiation protection is necessary. An interesting point: radiation exposure is actually dose-dependent in complex ways. Low doses of radiation can actually trigger repair mechanisms in cells, but high doses cause damage. There's a concept called hormesis, where low doses of stress can make organisms more resistant, but there's also just direct damage from high radiation doses. So understanding the radiation environment is important for designing both protection systems and potentially for understanding health effects. The lunar geology more broadly is also interesting scientifically. The moon has a history that's written in its rocks. Impact craters tell you about the intensity of bombardment over time. Different rock types tell you about the moon's internal structure and geological evolution. By collecting samples from the South Pole, which is a different region than where Apollo landed, we'll get information about the moon's geology in an area we haven't directly sampled before. An obscure fact: the moon's South Pole might be younger than other regions. Some of the craters there might be relatively recent impacts. Recent in geological terms, meaning in the last billion years or so. That means the regolith composition might be different from the equatorial regions where Apollo landed, so we might find completely different rock types and potentially different water ice compositions. There's also the question of the moon's internal structure. Seismic instruments left by Apollo astronauts recorded moonquakes, but those instruments eventually failed, and we haven't had seismic data from the moon in decades. Artemis missions plan to leave seismic instruments that will record vibrations from moonquakes and impacts, giving us information about the moon's interior structure. That tells us about whether the moon has a molten core, what the composition of the interior is, how the moon evolved. Now let's talk about the international science contributions to Artemis, because this is another interesting aspect. The Gateway, the space station that orbits the moon, is being built by multiple countries. Japan is building a power module. Europe is building a habitat module. Canada is building a robotic arm. These aren't trivial contributions, they're major pieces of the infrastructure. This means that scientists and engineers from multiple countries are involved in the mission. They have instruments on the landers. They have experiments in the habitats. They have priorities that they want the mission to address. So while Artemis is nominally an American program, it's actually an international program in practice. This has some interesting implications. It means that scientific discovery from Artemis will be shared internationally. Data will be published in scientific journals and made available to researchers around the world. It means that the knowledge gained benefits humanity as a whole, not just the United States, which is actually kind of the ideal of science, that we're advancing human knowledge collectively. But it also means that there are tensions and negotiations about priorities and resources. If Japan contributes a major module, Japan expects influence over how that module is used and what science is conducted. If Europe contributes equipment, European scientists expect opportunities to conduct experiments. NASA has to manage all these relationships and expectations while keeping the mission focused and on budget. Here's an interesting historical note. The International Space Station has actually been a successful model for this kind of international cooperation. Multiple countries contribute modules and components, and while there's definitely politics and negotiation, it's worked reasonably well for over 20 years. The Gateway is being designed on a similar model, hopefully learning from the ISS experience. But the moon is further away and more remote, so the dynamics are different. Now let's talk about some of the technological innovations that Artemis is driving, because space exploration has always been a driver of technological development. The spacesuits for Artemis are completely redesigned from Apollo spacesuits. Apollo suits were basically pressure suits. They kept the astronaut at pressure and provided oxygen, but they were heavy and hard to move in and hard to put on and take off. The new Artemis suits, called EXIMUS, Exploration Extravehicular Mobility Units, are designed to be more flexible and easier to use while still providing pressure and thermal management. An obscure fact: one of the challenges with spacesuits is that they get hotter as the astronaut does physical work. The suit has to dissipate heat. And in the vacuum of space, the only way to dissipate heat is through radiation. The suit has water cooling loops that transfer heat away from the astronaut to the outer surface of the suit, where it can radiate into space. But if the astronaut is working hard, they generate more heat than the suit can dissipate. So there's a balance between mobility, heat generation, and heat dissipation that drives the suit design. The XEMU suits also have better visibility than Apollo suits. The helmet design gives astronauts a wider field of view. There are lights integrated into the suit. There's a camera so mission control can see what the astronaut is seeing. These seem like small details, but for safety and for science, being able to see better and communicate better is important. The suits also have better mobility in the shoulders and hips. Apollo suits were notoriously restrictive. Astronauts had trouble bending and moving. The new suits use advanced materials and joint designs that allow more natural movement, which matters because astronauts are going to be doing more physical work on Artemis: drilling, collecting samples, setting up equipment. They need suits that don't restrict them. There's also been innovation in life support systems. The suits have their own life support backpack that provides oxygen, manages carbon dioxide, regulates temperature, and provides water for cooling. The backpack needs to be lighter and more efficient than Apollo backpacks because astronauts are going to be outside for longer periods. Another innovation is in the landers themselves. The landers use advanced materials that can handle the thermal stresses of landing and launch multiple times. They use advanced navigation systems that can guide the lander to specific terrain. They use advanced sensors that can assess landing site hazards and avoid them. All of this represents significant technological advancement over the Apollo landers. The Gateway and the orbital infrastructure also require innovations in power systems, communication systems, attitude control, and life support. These are things that NASA and its contractors are developing, and many of them will have applications beyond lunar exploration. There's been a lot of innovation in robotics too. The Gateway will have robotic arms developed by companies like Maxar that can move cargo and assemble equipment. These aren't humanoid robots. They're specialized arms and grippers designed for specific tasks, but they represent advances in robotic manipulation in space. One interesting development is the use of 3D printing and in situ manufacturing for space. There's been research into using lunar regolith as a building material, either sintering it with concentrated sunlight or mixing it with a binder. There's been research into 3D printing structural components in space using various materials. The idea is that eventually you could manufacture things on the moon or in space rather than launching everything from Earth. An obscure fact, some of the manufacturing techniques being developed for space have applications on Earth. Additive manufacturing, 3D printing, was actually developed with space applications in mind. Microgravity manufacturing allows you to create materials and objects that you can't make on Earth because gravity interferes. So there's a two-way knowledge transfer between space exploration and Earth-based manufacturing. Now let's talk about the broader implications of Artemis for the future of human spaceflight and space exploration. The most obvious implication is that lunar exploration is resuming at a scale and intensity that hasn't happened in 50 years. If Artemis succeeds, if the program maintains funding and political support, then there will be humans on the moon regularly. Maybe not continuously, but regularly enough that a presence on the moon becomes normal rather than exceptional. That changes how we think about space. For the Apollo era, going to the moon was the pinnacle of human achievement. It was the ultimate goal. For Artemis, going to the moon is a stepping stone. The vision articulated by NASA and other space agencies is that the moon becomes a base for further exploration of the moon itself, but also as a jumping-off point for Mars and beyond. This is where things get speculative, but it's worth thinking about. If you can establish a sustained presence on the moon, you can develop and test technologies that would be necessary for a Mars mission. You can practice long-duration spaceflight. You can practice living and working on another world. The moon becomes a training ground for deeper space exploration. An interesting comparison. Antarctica is a harsh, remote place on Earth. Early explorers went there, did science, and came back. But now there are permanent research stations in Antarctica. Scientists winter over, live in there for months at a time. They conduct research that's only possible in Antarctica. The station requires resupply missions, but they're regular and sustainable. The idea is that the moon could eventually be something like that, a remote research station where humans spend extended periods doing science and development. But there's a difference. Antarctica is still on Earth. Help is theoretically available. You can get emergency evacuation in days. The moon is different. You're not just remote, you're on another world. The engineering challenges and the risks are different. The Mars question is interesting because it informs thinking about Artemis. A crewed mission to Mars is generally thought to be 10 plus years away at the earliest, and that's optimistic. It's a much longer mission than going to the moon. We're talking about 6 to 9 months of travel each way, plus months on the surface. It's going to require technologies and capabilities that we either don't have yet or haven't tested at the scale needed. The moon becomes a place to develop those capabilities. For example, you could test long-duration life support systems on the moon before relying on them for a Mars mission. You could test in situ resource utilization, mining and processing local materials, on the moon before trying it on Mars. You could test habitat, designs, medical protocols, psychological support systems. The moon is a lower risk testbed for technologies and procedures that will be necessary for Mars. An obscure fact: the psychology of a Mars mission is actually a major concern. A crew going to Mars will be isolated from Earth for years. They'll experience extreme environmental stress, radiation, isolation, danger. They won't be able to get emergency evacuation. The psychological resilience required is different from what's needed for a moon mission or even the ISS. So some researchers think that the extended moon missions planned for Artemis could be valuable for understanding how humans respond psychologically to extended isolation and confinement. But here's the thing: Mars missions are not part of the official Artemis architecture. Artemis is focused on the moon. Mars is a separate goal that NASA talks about in the context of long-term human spaceflight strategy, but there's no funded program to develop Mars landers or Mars habitats the way there is for the moon. So while the moon could theoretically inform Mars exploration, there's a gap between the moon program and the Mars program that hasn't been bridged yet. The other implication of Artemis is that it's going to create a commercial market for lunar services. If NASA is regularly contracting with companies to deliver cargo to the moon, then those companies have an incentive to improve their systems and reduce costs. If multiple companies are competing for those contracts, then you get innovation and efficiency. Over time, this could lead to a genuine commercial lunar economy where private companies are doing more than just carrying cargo. They're mining, they're building habitats, they're offering services. This is still largely theoretical because the commercial lunar economy doesn't really exist yet. But the early signs are interesting. Several companies have expressed interest in lunar logistics and eventually in lunar resource utilization. Blue Origin, led by Jeff Bezos, has explicitly stated that its long-term vision is for a thriving commercial space economy, with the moon as a major hub. SpaceX is developing Starship with applications for lunar missions and beyond. Smaller companies are developing landers and rovers and other equipment. Whether this actually happens depends on economics. For mining and manufacturing on the moon to make sense, you need either a market for lunar products, like helium-3 for fusion, or metals and materials, or you need to use lunar resources to support further space exploration, building spacecraft from lunar materials, for instance. Right now, neither of those is economically viable. But the thinking is that as technology improves and costs come down, it could become viable. An interesting wrinkle: there's a question about property rights on the moon. The Outer Space Treaty says that no nation can claim sovereignty over the moon, but it's unclear whether private companies can claim property rights or mining rights. Some countries argue that resources extracted from the moon are the property of the extracting company. Other countries argue that lunar resources are the common heritage of mankind and can't be privatized. This is going to be a major legal and political question as commercial lunar activities increase. The Artemis Accords, which I mentioned earlier, actually include language about this. Countries that sign the accords commit to recognizing property rights for resources extracted in safety zones around landing sites. The idea is that if you land on the moon and establish a safety zone, the resources you extract within that zone are yours. This is controversial because it's kind of creating property rights on the moon despite the Outer Space Treaty saying the moon can't be claimed. But it's also pragmatic. If companies can't have property rights to the resources they extract, they have no incentive to invest in extraction infrastructure. So, creating a framework that allows property rights while still respecting the principle that the moon as a whole isn't anyone's territory might be the best compromise available. Now, let's talk about the environmental and resource implications of lunar exploration, because this is something that doesn't get talked about much, but is actually important. First, there's the question of space debris. Every launch creates potential debris. Rocket stages, discarded equipment, damaged spacecraft, all of this can become debris that orbits Earth or travels to the moon. Debris in orbit is a hazard because it travels at high velocity and can damage other spacecraft. There are already millions of pieces of debris in Earth orbit. NASA and other space agencies are working on debris mitigation strategies, but it's a long-term problem. For lunar missions, debris is less of an immediate problem because the moon is large and hitting it is relatively easy. But if you're leaving equipment on the moon, you want to make sure you're not creating hazards for future missions. There's also the question of planetary protection. When you send spacecraft to other worlds, you want to make sure you're not contaminating them with Earth microbes. Conversely, if you're bringing samples back from the moon or another world, you want to make sure you're not bringing back anything that could be a biohazard on Earth. Artemis has protocols for both of these concerns, but they add complexity and cost to the missions. An obscure fact: the moon is actually relatively dead microbiologically. There's no evidence of life on the moon, and the conditions are so harsh that it's hard to imagine Earth microbes surviving there. But we still follow planetary protection protocols because they're good practice and because you never know what you might find. There's also the question of protecting scientifically interesting areas on the moon. If you're trying to search for signs of past or present life, or if you're trying to study pristine geological features, you don't want human activity contaminating those areas. So NASA designates certain areas as special regions where activities are restricted. This creates a tension between exploration and preservation. You want to explore the moon, but you also want to protect its scientific value. The other environmental consideration is on Earth. Space launches have environmental impacts. Rockets burn fuel and create exhaust that goes into the atmosphere. Solid rocket boosters create particulates. Liquid-fueled rockets create different exhaust products. The environmental impact of space launch is relatively small compared to other human activities, but it's not zero, and it could increase as spaceflight becomes more frequent. There's been research into more environmentally friendly rocket propellants. Some companies are developing engines that use methane, CH4, or other fuels that have lower environmental impact than traditional rocket fuel. SpaceX's Raptor engines, which will power Starship, use methane and liquid oxygen, which is cleaner than some traditional propellants. But the fundamental issue is that launching anything into space requires energy, and that energy has environmental costs. Now let's talk about some of the challenges and criticisms of Artemis that are worth understanding. The cost is the biggest criticism. $100 billion over a decade is a lot of money. People argue that the money could be better spent on problems on Earth. And that's a fair argument, even if you don't necessarily agree with it. But there's also criticism about specific aspects of the program. One criticism is that the SLS is expensive and inefficient compared to commercial alternatives. Some engineers argue that you could do the same things with SpaceX Falcon heavy launches for a fraction of the cost. This is technically true for cargo missions, but less true for crewed missions because human rating adds cost and complexity. Another criticism is that Artemis is moving slowly. It's been over a decade in development, and we've only had one uncrewed test flight. The schedule keeps slipping. Artemis 2 was supposed to fly in 2021, then 2023, now it's 2025 or 2026. That's a pattern of schedule slips that suggests the program is not as efficient as it could be. There's also criticism about the international aspects. Some people argue that NASA should be doing this, not relying on international partners and their priorities. Others argue that international cooperation is inefficient and creates political complications, and there's definitely some political concern about sharing technology and information with other countries. There's also skepticism about the long-term vision, the idea of sustained lunar exploration and eventually lunar bases is compelling, but it requires long-term political and financial commitment. If budgets get tight, if administrations change, if priorities shift, the whole program could be scaled back or canceled. We've seen this happen with space programs before. The space shuttle was supposed to be routine and frequent and inexpensive. It turned out to be expensive and risky and never lived up to its promise. There's concern that Artemis could follow a similar path. An obscure fact: the Space Shuttle program actually illustrates how space exploration can become expensive and inefficient if not managed well. The shuttle was supposed to launch dozens of times per year and cost a few $1 million per launch. It ended up launching only a handful of times per year and costing hundreds of millions per launch. The reasons are complex. The engineering turned out to be harder than expected. Safety requirements were more stringent than anticipated. The launch infrastructure was more complex. But the fundamental lesson is that space exploration is hard and expensive, and costs tend to exceed projections. This is relevant to Artemis because there's an assumption that sustainable lunar exploration is possible with the budget and timeline that's been proposed. But if history is any guide, costs could increase and schedules could slip further. There's also criticism about the science-to-cost ratio. For $100 billion, how much scientific knowledge are you actually gaining? The moon is scientifically interesting, but we've already learned a lot about it from orbital instruments and sample analysis. Some scientists argue that you could learn more about the moon for less money by sending more robotic missions instead of crewed missions. This is actually a fair point. Robotic missions are cheaper and can in some ways be more capable than human missions. A rover can travel much further than an astronaut in a spacesuit. A spacecraft can have more instruments than an astronaut can carry. But there's also a role for human judgment and adaptability that robots don't have. A human can see something interesting and change the plan. A human can troubleshoot problems creatively. So there's a debate about the optimal mix of robotic and human exploration. Another criticism is that Artemis is perpetuating a tradition of space exploration that benefits wealthy countries and spacefaring nations. The moon missions are expensive and require access to advanced technology and significant financial resources, so they're accessible to the United States, perhaps to China and Russia and Europe, but not to most of the world's countries. Some people argue that resources would be better spent on making basic needs: food, water, healthcare, education, accessible to all humans before we go back to the moon. This is a values question again. Different people prioritize different things, but it's worth acknowledging that space exploration is an activity of privileged countries and does represent a use of resources that could be used elsewhere. Now, let me talk about what success looks like for Artemis and what failure looks like, because understanding the criteria for success is important. Success would be Artemis 2 flies safely with 4 astronauts to the moon and back. Artemis 3 lands astronauts on the moon near the South Pole, where they spend multiple days conducting science. They collect samples of water ice and regolith. They set up instruments and habitat components for future missions. They return safely to Earth. The mission leads to scientific discoveries about the moon's geology, water resources, and radiation environment. The mission opens the door to sustained lunar exploration with additional Artemis missions. Failure would be the SLS or Orion has a critical failure that prevents the missions from flying or that endangers the crew. Schedules slip so far that political support collapses and funding is cut. The cost overruns become so severe that Congress cancels the program. A crewed mission results in loss of life. Scientific return doesn't justify the cost in the eyes of the public and policymakers. Right now, we're in the early stages. Artemis 1 succeeded, which is good. Artemis 2 is the next test. If that flies successfully, then Artemis 3 becomes more likely. But there's still risk and uncertainty. One scenario that people worry about is a partial success that doesn't quite meet expectations. For example, what if Artemis 2 flies, but there's a minor issue that causes schedule delays? What if Artemis 3 lands on the moon, but the astronauts have equipment failures that limit scientific activities? What if the mission succeeds technically, but doesn't generate the public interest and support that was hoped for? These partial successes could lead to a slow decline of the program, not a dramatic cancellation, but a gradual reduction in scope and ambition, which would be a kind of failure, even if it doesn't look dramatic. On the other hand, what if Artemis succeeds beyond expectations? What if the missions are scientifically productive and generate enormous public interest? What if the technology works so well that subsequent missions can be more ambitious? What if international partnerships lead to additional missions and a genuine international presence on the moon? That's the best case scenario, and it's possible, but it requires things to break right and for political and financial support to hold up. Now let's talk about what comes after Artemis in the vision of lunar exploration. This is speculative, but it's interesting to think about. If Artemis succeeds, the next phases would involve longer missions, more astronauts, more equipment left on the moon. You could imagine a scenario where, by the 2030s, there are regular missions to the moon with crews staying for weeks at a time. You could imagine equipment being deployed, habitats, power systems, laboratories, mining equipment. You could imagine the beginnings of a real infrastructure on the moon. The gateway would become increasingly important as a hub. Cargo would come up from Earth to the gateway. Landers would ferry cargo and people from the gateway to the surface. Equipment would be assembled and tested at the gateway before being sent to the surface. You'd have a supply chain operating between Earth and the moon. One interesting scenario that's been discussed is a lunar village concept. This would be a semi-permanent settlement on the moon, where different countries and organizations contribute modules and equipment. Different nations would have different areas of responsibility. It would be loosely coordinated, but not under a single authority. It would grow organically as different countries and companies added capabilities. This is different from a lunar base, which would be more of a centralized, organized operation. A village suggests more distributed decision-making and contribution. Whether this would actually work in practice is unclear, but it's conceptually interesting. There's also the question of what activities would happen on the moon. Scientific research is obvious: geology, astronomy, search for life. But there could also be technological development, testing new materials, manufacturing, 3D printing. There could be resource extraction and processing. There could eventually be tourism, wealthy individuals paying to go to the moon. There could be manufacturing or other commercial activities. An interesting proposal that's been discussed is manufacturing on the moon. Some materials or products might be easier to manufacture in low gravity or vacuum than on Earth. For example, certain types of crystals or fibers might grow better in microgravity. Pharmaceutical products might be manufactured in space where you have perfect vacuum and microgravity. If you could manufacture these products on the moon or in lunar orbit and then ship them to Earth, you might have a valuable product. This is very speculative and depends on developing markets and technologies that don't exist yet, but it's the kind of thinking that informs long-term visions for space. There's also been discussion of using the moon as a stepping stone for resource extraction to support space exploration. The idea is that you mine the moon for water and metals. You use those resources to build spacecraft and habitats in space, and you avoid the enormous cost of launching everything from Earth. This would require developing mining equipment, refining equipment, and manufacturing capability, all of which would be expensive and challenging. But if it worked, it could dramatically reduce the cost of space exploration. An obscure fact: some of the most detailed thinking about lunar mining and resource utilization has come from organizations like the Lunar and Planetary Institute and academic researchers, rather than from NASA or space agencies. These researchers have done detailed engineering and economic analyses of what it would take to mine the moon profitably. The conclusions are generally that it's possible with the right technologies and markets, but it's not imminent. We're talking about decades of development before lunar mining becomes a reality. Now let's zoom out and think about the bigger picture. What does Artemis represent in the context of human history and human civilization? On one level, it's a continuation of exploration. Humans have always been explorers. We've explored our continents, crossed oceans, climbed mountains, gone to the poles. Going to the moon and building a presence there is a continuation of that impulse to explore and to push the boundaries of where humans can go. On another level, it's about technological capability and achievement. Artemis demonstrates that we have the knowledge, the engineering, and the resources to accomplish something extraordinarily difficult. That's valuable for its own sake. It pushes the boundaries of what we think is possible. On another level, it's about inspiration and meaning. Space exploration captures people's imagination in a way that few other things do. When the Apollo missions happened, they inspired millions of people, especially young people, to pursue careers in science and engineering. They changed how people thought about themselves and their place in the universe. Artemis could do the same thing. There's also a geopolitical dimension. Space exploration has always been entangled with international competition and national pride. The space race was fundamentally about competition between the United States and the Soviet Union. Artemis is different. It's more collaborative and less about competition, but there's still national interest involved. Countries want to demonstrate their technological capability. They want to be involved in major space exploration efforts. They want to be part of humanity's future in space. There's also the question of why we do this at all. Why spend hundreds of billions of dollars to go to the moon when there are problems on Earth that need solving? This is a question that space explorers have grappled with since the beginning of space exploration, and the answers are multiple. One answer is that exploration and problem solving aren't mutually exclusive. We can do both. The fact that we spend money on space doesn't mean we can't also spend money on healthcare or education or climate change. Another answer is that the knowledge and technology developed for space exploration have applications on Earth. The technologies developed for Artemis will eventually find their way into commercial use. Solar panels developed for space are now a major renewable energy source. Satellite technology developed for space is fundamental to modern communications. Materials science developed for space has applications on Earth. A third answer is that having a vision for the future, a goal to work toward, is valuable for civilization. Without goals like space exploration, we might be more focused on short term problems and less on long term thinking. Space exploration forces us to think decades ahead, to invest in capabilities that won't pay off for years, to believe in human potential. A fourth answer is that exploration itself is a fundamental human drive. We're curious. We want to know what's out there. We want to go places we haven't been. This drive has taken us across continents and oceans. Taking it to the moon and beyond is a continuation of something deep in human nature. I think the most honest answer is that it's complicated. Space exploration requires significant resources that could be used elsewhere, but it also provides value in ways that are hard to quantify, and different people weigh those factors differently. What I find interesting about Artemis specifically is that it's happening at a moment when space exploration is changing. For the first time, commercial companies are playing a major role in spaceflight. For the first time, multiple countries are collaborating on deep space exploration. For the first time, we're thinking about sustained presence on another world rather than just visiting. These are significant shifts from the Apollo era. I think the next 10 to 20 years are going to be really interesting for space exploration. We're going to learn whether humans can establish a sustainable presence on the moon. We're going to learn whether commercial space activities can actually work. We're going to learn whether international cooperation in space can succeed at scale. And those lessons will inform whether we go to Mars, whether we establish space settlements, whether space exploration becomes a normal part of human civilization, or whether it remains an exceptional achievement reserved for spacefaring nations. Artemis is the beginning of that story. It's not the end. It's not even the most ambitious thing that could be done, but it's a significant step, and it's worth paying attention to.